Hello everybody. This PAG focuses on determining an experimental value for G using three methods and then comparing the differences between the three experimental G values and why they are different from one another. We'll cover the equipment used, give step-by-step instructions on how to obtain the necessary data, and how to analyze the results afterwards. The first method involves holding a ball at a set height and manually starting a stopwatch at the moment of release, then stopping the timer as soon as the ball hits a soft pad at the bottom. The equipment used for this practical is as follows: a tennis ball, a clamp stand, a stopwatch, and a meter ruler. Hold the ball at a set height using your hand. As you release the ball, start the stopwatch and stop it as soon as the ball hits the floor. This works best with two people, one person to drop the ball and one person to time the fall. Record the height at which you dropped the ball from and record the time taken for it to fall this distance. Repeat the experiment at this height at least 3 times to validate your results. Reduce the height by a constant amount, for example 0.2 meters for each repeat, and repeat the experiment. Do this for a minimum of 6 different heights. The second method uses an electromagnet to hold a ball with a timer that is automatically triggered when the electromagnet is switched off and a contact pad to stop the timer. The equipment used for this practical is as follows: an electromagnet, a ball bearing, a clamp stand, a contact pad, a timer, a meter ruler, and a power pack. The ball is held at a set height using the electromagnet. When the electromagnet is switched off, it releases the ball and simultaneously starts the timer. When the ball hits the contact pad at the bottom, the timer stops. This gives the total fall time. Record the height at which you release the ball from the electromagnet and record the time taken for it to fall this distance. Repeat the experiment at this height at least 3 times to validate your results. Same as before, reduce the height by a constant amount each time, for example 0.2 meters for each repeat, and repeat the experiment. Do this for a minimum, again, of 6 heights. The final method uses a double interrupter card and a data logger to measure the acceleration directly from the card's fall, taking into account the start and end speed and the time taken between the interruptions. The equipment used for this practical is as follows: a double interrupter card, a light gate, a clamp stand, a data logger, and a TV screen. We are using the Data Harvest Vision data logger. To calculate acceleration directly from the light gates, first load up the data logger and go into the timing function. Once loaded, select the acceleration option, then measure acceleration at A. Then the double interrupter card option. Next, set the length of the double interrupter card to be however long your card segment is. Ours is automatically set to 40 millimeters. Then set the decimal places for all the quantities to what you see on screen. And finally, select the columns to display the acceleration at A. Once finished, your data logger should load the correct graph, and you can start. Hold the double interrupter card above the light gate and simply drop it through. The data logger will do the rest for you. Make sure that when you drop the card, both interruptions pass through the light gate, and you don't throw the card through the light gate, as this will not give you an accurate value for G. This is an example of the data you should receive for the manual method. Don't forget, when recording your data, to keep to the same number of decimal places and significant figures. For example, the table above is consistent with 2 decimal places. Put your units in the headings at the top and keep your tables nice and clear, with lines to separate each reading. To calculate G, we use the SUVAT formula S equals UT plus half AT squared. Since the ball starts from rest, U must equal 0 meters per second, so this can be simplified to S equals half AT squared. We can relate S equals half AT squared to Y equals mx, and if we plot S on the y-axis against t squared on the x-axis, the gradient of the line equals half a. So to find G, all we need to do is multiply the gradient by 2. For this data, we get an experimental value for G of 9.4 meters per second squared. While this method is quick and simple to set up, it is very prone to human errors in the reaction time of timing the stopwatch, hence giving us a reason for why our experimental value is not close to the true value of G. This is an example of the data you could receive for the electromagnet method. Depending on how much time you have, you can adjust the height of the electromagnet and record extra readings for the time to fall and plot another graph, similar to the one for the manual method, but in this instance we are just using trial data to compare experimental values for G. Using the same SUVAT method as before and having dropped the ball from a height of 1.78 meters, we get an experimental value for G of 9.57 meters per second squared. While this experimental value is more accurate than the manual method, since reaction time is taken out of the equation, there will still be a small time delay in the electromagnet release, making the fall appear longer and hence a lower value for G, as well as uncertainty in the timing, because if the timer starts or stops a fraction too early or too late, T will become inaccurate. This is an example of the data you could receive for the data logger method. Since it calculates the acceleration directly for you, we do not need to change the height at which we drop the card. We simply repeat the drop however many times we wish to then get an average acceleration. This experimental value will be the most accurate of the three, as we are using optical sensors to calculate acceleration, which will give a high digital precision as opposed to the electronic response time of the contact pad. And where the electromagnet may have a small timing delay, in either the timer being off or the electromagnet not releasing the ball at the exact moment the timer starts, the light gate will detect the exact moment the object passes through. Don't forget to calculate the percentage uncertainties in your measurements and the percentage differences between your experimental values for G and the real G values for all three methods. All three methods are generally low risk, but supervision, equipment checks, and good setup practices will ensure safety and the ease of clearing away. The risks for each method include the risk of electric shock from equipment, which can be mitigated by checking the electrics are safe before switching on, the risk of a ball bearing falling and rolling away, which can be mitigated by implementing a catch tray for the ball to fall in, risk of tripping over wire cables in an electrical setup, which can be prevented by having a generally organised setup, risk of the electromagnet overheating, which can be prevented by testing the equipment before use to make sure it functions as intended, finally, a risk of the clamp stand toppling over due to excess equipment on the stand, which can be prevented by using a G-clamp to secure the stand to the table.